Hello, Chem 1B. This is Chapter 17, Lecture Video 1. We're going to be talking about aqueous equilibria. And really, this chapter is almost like Chapter 16 continued. We're still going to be talking about acid bases, as well as solubility and one other type of equilibria. But we're also going to be talking more specifically about buffers in this chapter, and that's what most of this chapter is about. So what is a buffer? A buffer is an acid-base solution where pH is maintained in a stable fashion. So what that means is if I add a strong acid to a buffer solution, it will not really change the pH very much as long as I add small amounts. Buffers are super important to a lot of systems. In biology, they keep our blood at the correct pH range. In our other organs as well, we have usually buffers throughout our body, keeping the pH at what it should be. Because if pH gets too high or too low, cells kind of die, which would be bad for us. So how are buffers made? They contain significant amounts of a weak acid and its conjugate base. So basically we have a large concentration or a significant concentration of weak acid present in the solution, and at the same time we also have a significant concentration of its conjugate base. Or we could flip that, right? We could have a weak base present at a significant concentration and its conjugate acid also present at a significant concentration. In both cases, we have a buffer. As soon as we have a conjugate pair, both present in a significant way, we have a buffer system. Now, what happens is when we add strong acid to this buffer, it will react with some of the base in the buffer solution, converting it back to the acid form, which mitigates the effect on pH. And when we add a strong base, it reacts with the weak acid present in the buffer, converting that to the basic conjugate, which also keeps pH from changing very significantly. As long as we still have significant concentrations of both the weak acid and the conjugate base after adding a strong acid or a strong base to the solution, we still have a buffer and pH will only change slightly. So let's look at some buffer solutions. This solution here where we have formic acid and sodium formate is a buffer. So if we have a solution that has 0.5 molar both of sodium formate and formic acid, we have a buffer system. Now, formic acid will react with any strong base. So kind of going back to what I just talked about, right? If I add a strong base to this buffer, the base will react with the acid. The formic acid will form more formate, which is our conjugate base, CHO2 minus 1, and water, which is whatever. In this case, as long as the base is the limiting reactant in this reaction, notice it's a one-way arrow. That's important. This reaction will still have a buffer at the end if our KOH is our limiting reactant. Now, we always assume neutralization reactions between a base and an acid, a strong base and a weak acid, or vice versa, or whatever, is going to be a reaction that goes to completion, and it's not going to be an equilibrium step. This is not an equilibrium reaction. After this reaction, we have a second equilibrium occurring that we would need to solve eventually. The formate, the CHO2, can actually react with an acid, right? So let's use a strong acid, let's say nitric. This again, one-way arrow. This is not an equilibrium reaction, it's neutralization. Neutralization reactions go to completion. So the acid here is going to react with the sodium formate, or specifically the formate in sodium formate. Sodium is actually a spectator ion, if you remember your net ionics from Chem 1A. And we form formic acid as a product, which is the conjugate acid of formate. This, again, maintains a stable pH. As long as our strong acid here is the limiting reactant, we'll still have sodium formate present at the end of the reaction, and we'll have some formic acid present still. We'll still have a buffer. If this isn't the limiting reactant, we'll have destroyed the buffer. And the same thing for our KOH. So let's do a buffer problem, right? Which of the following solutions, we're going to say each species is at 0.5 molar, is not a buffer? Now, really what we need to be able to determine here is which two are a conjugate pair. That has to be true. And then the second thing is they have to be a weak acid and its conjugate base, or a weak base and its conjugate acid. At no point can we be dealing with a strong acid. So for instance, if I said, hey, we have HNO3 and NaNO3, this is not a buffer because HNO3 is a strong acid, and in order to form a buffer solution, you have to have a weak acid in its conjugate base or a weak base in its conjugate acid. Weak is a key word here. Now, if we look at all of our options here, this is a weak acid, and this is its conjugate, right? We got acetic here, and we have sodium acetate. Acetate is the conjugate base of acetic acid. So this is a buffer. Here we have NH4 plus and NH3. These two are also conjugates. So that's a buffer. C is actually not a buffer. All right, so we have phosphoric acid, which is a weak acid, but the conjugate base of phosphoric acid is H2PO4 minus. And if we had sodium dihydrogen phosphate, which is what this polyatomic is, then sure, buffer, but we don't. Notice there's only a one hydrogen here, so this is monohydrogen phosphate, and that is not the conjugate of H3PO4. It's actually the conjugate of this guy. So this is not a buffer, which means it's our correct answer. If we look at HNO2, its conjugate would be NO2 minus. Hey, look at that, buffer. HIO, NaIO, also conjugates, also weak, also a buffer. So the only one that's not a buffer, and therefore our answer is C. Okay. So let's look at calculating the pH of a buffer solution. So when we calculate pH, we need to understand that we have 0.5 molar in this case, right, of formic acid and sodium formate. Now, sodium formate, this guy, it contains a weak base. So this is a basic salt. And really, we don't care too much about the Na, right? Really, I just care about the CHO2 minus present in solution. Now, when we do problems like this, we want to calculate H3O plus, we want to calculate pH, and this is an equilibrium problem. Now, we could technically use the weak base equilibrium for a Kb of formate, or we could use the Ka for formic acid and use its equilibrium. It doesn't really matter. However, since we want pH, we probably would rather have the reaction that has H3O plus in it. So I'm going to use the Ka equilibrium for formic acid. Now, at this point, I can do an ice table, right? So if I look at this problem, I have my equilibrium here. I was told that I had 0.50 molar of this and 0.50 molar of that guy. Now, if I do that ice table, I can set that up, right? I know I don't care about water. H3O plus initially is 0, but formate, CHO2 minus, I was told we had 0.5 molar of sodium formate in there, so we have 0.5 molar formate. Now at this point, it's just a regular equilibrium problem, nothing different from what we've seen before. We do our change, we add initial and change rows, we get 0.5 minus x, 0.5 plus x, and we can set this all equal to our equilibrium constant because we were given that here. and solve for X. And X will be equal to our H3O plus concentration. Now, I am definitely going to be using the 5% rule here, so I'm going to cross off the plus X and minus X. This basically tells me that X is equal to Ka, right? Because 0.5 divided by 0.5 is 1. 1 times X is equal to 1.8 times 10 to the negative 4. At this point, I can now calculate my pH because we just take the negative log. Remember that X here is equal to our H3O plus concentration. So negative log of X gives me our pH here, which is 3.74. Now, if these two weren't at the same exact concentration, we would have a different value than the Ka as our X. This is not always the case, right? But generally, the closer these two things are to equal, the stronger our buffer system will be. So, just to kind of summarize, a weak acid will ionize on its own, right? So if you look at formic acid, right, HCHO2, this guy, if we had 0.5 molar of it, it would have its own pH, and that pH would be 2.02 by itself. The base, if I just had sodium formate present, right, if I had just by itself NaHCHO2 at 0.5 molar, I'm going to have a basic pH here because that's a weak base, and its pH would be 8.72. However, when we just did this calculation, when we have both of them present, our pH is 3.74, higher than the acid by itself and lower than the base by itself, which hopefully kind of makes sense. We have an acid and a base present. They're going to mitigate each other a little bit. However, this is much closer to the acid than it is to the base. So the question then is, why? Right? Well, the answer to that question is, well, formic acid is a stronger acid than sodium formate is a base. Sorry, I just realized I wrote sodium formate's formula wrong. It should just be Na here. As you can see, like if we look at the Ka of this, it's 1.8 times 10 to the negative 4. I think the Kb of this is like 5.56 times 10 to the negative 11. So this guy's much stronger than this, which is why our pH, when we have a buffer of both of them present, is much closer to the acid region than the base region. All right, so that's pretty much the end of this video. If you have any questions, as always, please email me or come to the discussion sessions.